15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello to you once again. Thank you for joining us on the podcast we call Space Nuts. My name's Andrew Dunkley, and with me as always, Professor Fred Watson. Hello, Fred.
Hello, Andrew. How are you doing?
I'm much better than I was last week. I'll be.
That's good.
I'm pleased to tell you. Yes.
Well, I'm very happy to hear it.
Got over my cold and ready to take on the world. Comets and all. And we're going to be talking about that because there's been some new evidence put forward about so-called hyperactive comets and Earth's water, which is fascinating reading and should be good to talk about. We're also going to look at the 100th anniversary of a significant eclipse. And we've got a couple of questions. One from Bo about dark energy versus dark matter. He's come up with an interesting idea on both of those situations and the expansion of the universe. And Christian is asking us about DNA seeding in the universe. That really is an interesting question too. So we'll tackle those a little later. But first, Fred, there's always been this theory surrounding how Earth got its water. And, of course, the strongest theory is based on comets shedding their water at impact and flooding the Earth, basically. But there's a problem with that theory until now.
Well, it might still be there, but there's new light on it, put it that way. New light has been shed on comets. So you're quite right. It is a very popular idea among scientists that the icy objects that we see today as comets that sort of come in from the outer solar system in very elongated orbits, we know that they're mostly made of ice. Was once described as dirty icebergs, and that's kind of what they are, because they're sort of ice with a lot of dust embedded in it, basically. And that's why when they get near the sun's energy drives off the ice, it evaporates or actually sublimes, turns straight into a gas in the vacuum of space. And so you get this plasma tail from the comet being blown away by the solar wind. But you also get a dust tail. Comets have two tails. One's the plasma, one's the dust. And that's why they're really spectacular sometimes. So we know that they're mostly ice, and it's a very neat and tidy theory. Oh, sorry, let me just make another step in that argument. We also know that they've hit the Earth from time to time, because the Earth, in its history, as we now know very well, has been bombarded, like every other object in the solar system at some time or another, been bombarded by space debris, usually in the form of asteroids, but also comets as well. And it's possible that comets actually have had quite a big effect on the history of the Earth. We know that there were more of them in the early history of the solar system. That's going back 4.5 billion years. And so the suggestion has been that when the Earth cooled enough and its climate got sensible enough for it to have liquid water on the surface, that the ice that had been deposited there by, probably 1 billion years of comet impacts or something like that, maybe a little bit less than that, perhaps 500 million years, but a long time of comet impacts, that ice actually turned into liquid and gave us our oceans. So that's the basic theory. But the problem, you correctly said at the beginning, there is a problem with this. And it's all about isotope ratios. And isotope ratios crop up quite often in our discussions because they can be the fly in the ointment. It's actually one reason why we struggled for a long time with the idea that the moon was formed by a collision with by the Earth with a smaller object called Theia. And that's and that was scuppered for a while anyway by the fact that the moon's rock and the Earth's rock have exactly the same oxygen isotope ratios, and that doesn't work with some of these theories. There is one that we talked about that it does, but we can't go there because we're on a different story. Indeed. So the same is true. Bring me back, Andrew, bring me back. The same is true of comets. So it turns out that there is a sort of mix in the water of the oceans on Earth, and a mix in the ice of comets between two different kinds of water. There's normal water, which is made from normal hydrogen atoms, but there is also something called heavy water, in which the hydrogen atom in the H2O molecule is actually an atom of what's called deuterium, or heavy hydrogen. So it is hydrogen, but it's got an extra neutron in its nucleus. It's got one proton like normal hydrogen has, but it's got this extra neutron in it, which doesn't change its charge at all. And so it's the same stuff, it's hydrogen, but it gives it a slightly different atomic mass. And in fact, that's an isotope, a different isotope. And so it turns out that what you can do when you look at the water in the Earth's oceans is look at the ratio of normal water to heavy water, to this deuterium-rich water. And you get a certain ratio. I can't remember what it is. The normal water really outweighs heavy water by a large fraction in my recollection. But that's the difference with comets, because a lot of comets that have been analysed, whose makeup has been analysed, it turns out that they have much more of this heavy water, which has the deuterium version of hydrogen in it. So the ratio of heavy water to normal water is higher in comets. And that's been the puzzle, because these ratios are very, very stable. They don't sort of intermix and change. They stay.
So we've got water that a lot of comets couldn't have given us.
That's the bottom line. Yeah, because it's a different kind of water.
Okay.
Right. So then
So
the plot thickens, because observations of a comet by the name of 46P Wirtanen. It's a well-known comet.
Yep.
And
I think we've talked about that one before.
Yes, we have, and we may have talked about it in this context, but I don't think the results were out then. They've now been published. So it was observed by SOFIA, which you'll remember is NASA's Stratospheric Observatory for Infrared Astronomy, aka a Boeing 747 SP with a big hole cut in the back.
Oh, yes, I've seen. Yeah, we've talked about that before too, because we used the photo of it as a feature on the podcast. It's a
fantastic thing. One of my colleagues here has used it a couple of times, and he comes back and tells all these tales about jetting around the South Pacific. They're based in New Zealand when they come to the Southern Hemisphere. Wow. And he's a Kiwi, actually, so he hops across home and gets his time on SOFIA. Anyway, SOFIA, of course, can look in detail at what you call the far infrared region of the spectrum, because you're way above most of the Earth's atmosphere. And that lets you sense the content, the isotope content of the water being radiated by, being plasmarized, if I can put it that way, by a comet. So you can tell what it is. And it turns out that 46P Wirtanen, or Wirtanen it should probably be, because I think he was, if I remember rightly, he was Finnish with a name like that you'd expect. Anyway, I might be wrong there. That's the discoverer that I'm talking about. Now, I've gone off again. I don't know what it is, Andrew. I keep rambling today.
That's all right. We'll sort it out when we finish.
Yeah, I hope so. So get to the story, Fred. Well, this comet actually turns out to have the same isotope ratio as we have in the Earth's oceans.
Aha.
So
it's a smoking gun.
It's a smoking gun, that's right. And it turns out that there's a couple more comets that are the same. This is the third comet that's been, measured since we had this technology to show the matching deuterium balance that matches the Earth's oceans. And so what astronomers, of course, now look for is a common element between them. And there is one, because they all suffer from ADHD. Yeah. They're all hyperactive comets. And that description comes about because when they get near the sun, the amount of water vapor that comes off them is more than what can be produced by a comet of that size. In other words, the flying iceberg that the comet is not big enough to produce that amount of water vapor. And so
that just sounds weird.
It does sound weird. And the reason why it happens, apparently, is that the comet itself has a thin atmosphere of water vapor around it. which is released when the comet gets near the sun. So you're looking at a comet that's and that's why they call it hyperactive, because it's got more stuff coming off it than you can explain by the size of its nucleus. So there's clearly a link here between hyperactive comets and the kind of water we have on Earth. And I guess the suggestion is that this may mean that in the early solar system, when the water of the Earth was being collected by the Earth in the form of ice, things hitting the Earth, icy objects hitting the Earth, it suggests that there were more hyperactive comets around then, and they were the predominant, breed of comets with this isotope ratio. Okay. I think there's still a lot to learn about this, but it's one of the kind of closing sentiment of the research paper on this is that maybe all comets share the same Earth-like hydrogen deuterium ratio in water, rather than just a few of them sharing it, which is what we see now. Maybe in the early days they all shared that because of what we've discovered from Comet Virtanen.
Well, so that kind of kills my question, because I was going to say, if the wrong kinds of comets had struck Earth instead of the ones that obviously made up our water supply or part thereof, what would our planet be like now? It would have had a different isotope ratio. So heavy water would have been much more common than it is now. And would we have been able to live in an environment like that?
Yeah, that's a really good question. I'm not sure of the biological implications of heavy water. I think it's okay. I think you can probably drink it and swim in it and things like that. But I'll need to check that out. In fact, we should make that a question for next time, and I'll try and remember to look it up.
We'll save someone else writing into us, because someone will ask.
Yes, they will. Yeah.
Okay, I will write a note.
Write a note and send me an email. Check out heavy water.
We'll see if we can figure that one out. Okay, fascinating though. They found a smoking gun that may answer the question as to how water got on our planet, which is very good news indeed.
It would be, yeah. It would be nice to solve that one.
Yes. Well, they're getting closer by the sound of it. You're listening to Space Nuts. Andrew Dunkley here with, of course, Fred Watson.
Roger, you're allowed to clear here also.
Space Nuts.
Now, Fred, we're going to look at a significant anniversary, or an anniversary of a significant event, I think would be more accurate, the 100th anniversary of an eclipse. Now, that probably seems strange because they're all too regular, and people often ask questions about how we know when they're going to happen, etc., etc. But in this case, it involves Albert Einstein.
Indirectly, that's right. So this eclipse, so we're recording this as we speak on the 28th of May, and tomorrow, the 29th of May, is the 100th anniversary of the eclipse that really changed the world of astronomy, because it was the eclipse that essentially demonstrated the truth of Albert Einstein's general theory of relativity, which you might remember was formulated, he published it late in 1919, in the middle of the First World War, which turns out to have a little bit of an effect on the story. But what happened was he'd worked on his theory of relativity for a number of years before it was published in 1915. And one of the things that was suggested as a way of proving it was observing the sun during a total eclipse. And the reason for that is that the general theory of relativity says that any massive object distorts the space around it. Mm-hmm. And whereas Newton had said gravity works by the force between two massive objects, or one massive object and lots of not massive ones, as we've got here on the Earth. But Einstein's theory says, no, that's not what it is. What happens is gravity is bending the space around the object. And you feel that bending as a pull, as a gravitational pull. So that's the essence of his theory. Now, just imagine how that will be greeted by a whole lot of physicists.
Well, 100 years ago, they would have thought it was a nutcake.
Yeah, exactly. That's exactly what they would have thought. So very early on in his theory, he knew he wasn't a nutcase, but nobody else did. Very early on in his theory, he thought of ways that it could be demonstrated, and one of them was the idea of looking at stars which appear close to the edge of the sun, and see whether their light is bent, see if they're moved out slightly out of their normal positions on the sky.
Yeah.
Of course, the only way you can do that is to blot out the sun, and the only way you can do that is in a total eclipse of the sun. And in fact, that idea was dreamed up probably 3 years before Einstein published his theory, because in 1914, a mate of his, who turns out to have a role in my own story, his name is a friend of Einstein's. His name was Erwin Freundlich, and he worked in the Berlin Observatory. And Freundlich was an astronomer, and he was dead keen to work with Einstein to measure an eclipse. So I think it's about August 1914, he set off to the Crimea to observe an eclipse that was going to cross that. And the First World War promptly broke out, and he was interred as an enemy alien.
Oh.
So he never made it. Poor old Freundlich was stuck in jail. What's the connection? I should just tell you what the connection is. Freundlich in 1939, actually in 1933, I think he fled Germany because he had Jewish origins, and I think he was married to a Jewish wife.
You could see the writing on the wall.
Yeah, he could. And he went via Czechoslovakia, as it then was. But he wound up in 1939 in Scotland at the University of St Andrews. And that's where I was educated.
Yes.
And it's a bit closer than that, because actually one of his students was a young Polish refugee, actually, by the name of Tadeusz Slibarski. And Slibarski was my master's degree supervisor. I did research on astronomy.
No kidding.
So Freundlich is my academic grandfather. There you
Fantastic.
go.
Oh,
That's
wow.
why. It's one reason why I love this story, plus the fact that he got himself locked up in the Crimea. I think he was released reasonably quickly. Anyway, the First World War kind of got in the way. So when the theory of relativity was published, of course, there was no chance of doing expeditions looking for eclipses because the world was in a state of conflict. So it was not until after the war that this Eclipse Expedition was mounted. Now, the other person in the story besides Einstein, who's key to this story, is a man called Arthur Eddington, who was at Cambridge Observatory. And Eddington somehow, I think it went through Belgium, the way this reached him. He had basically a preview of Einstein's theory that, it was the paper, I think, that Einstein had published it in, which was banned in Britain because it was published in a German journal. And by then, British and German scientists were absolutely at loggerheads. But through Belgium, Eddington got a copy of this paper. He's probably the only guy in the country who could understand it because he was a mathematician, and he realized that this was brilliant stuff. And so he kind of resolved, once the war was over, to try and set up an eclipse expedition, which he did with the Astronomer Royal and a few other people. This eclipse on the 29th of May 1919, the path of totality, the moon's shadow, went right across from South America all the way across to Africa, to southern Africa. And so he had two lots of observers, one set in Brazil and one set on the island of Principe, I think it's pronounced, or Principe, which is not very far off the African coast. And sure enough, they observed the eclipse and measured the deflection of the light of the stars, and it matched Einstein's prediction, which was, extraordinary. And so very soon after that, after they'd done all the data reduction and everything, there were headlines blared across all the papers, new theory of the universe. And basically a lot of public talks were given and all the rest of it. But the reason why it's really interesting and perhaps such a nice story is that it brought together the two warring sides. Because, as I said, during the time of the First World War, there was horrendous animosity between German and British scientists, as you might expect, but a lot of it was fake news. But you can read all about it. We've still got the journals, where all this stuff was written up. And they're all these Brits are saying, we can never trust the German science again. And yet, less than a year after the war, a British scientist had proved the theory of a German-born academic, Einstein. He was actually Swiss by nationality, but he was born in Germany. And it did a huge amount, to reconcile the two halves of the story, the British and German scientists. And maybe the other really nice thing about it is that both Einstein and Eddington were sworn pacifists. Einstein because of his Jewish faith, and Eddington was a Quaker. So he was an ardent pacifist. And, it was a great healer in terms of post-war science.
Well, so that's if scientists can't put their differences aside in the name of science, there's not much hope for any of us.
That's right. That's actually what they all said at the beginning of the war, but it only took a year before they said, well, we can't trust anybody. The war had an amazing impact on lots of things outside of science as well. Like, the reason they don't play cricket in Germany is because the Germans banned everything British. Yes, right.
The British changed the name of a dog from German Shepherd to Alsatian because of the war. I mean,
that's right. Well, know about that. You've written about the war in your.
But those little things just fascinate me, and I mean, it's understandable for the time.
Yes,
they're trying to just keep the sides completely separate. They're ideologically opposed, but they took it right down to sport and household pets
and dogs.
It was almost insane. But one thing I picked up during the course of your discussion there about Einstein's theory of general relativity being proved by this Eclipse expedition. It sounded akin to what we've talked about before in terms of gravitational lensing. Would that be a fair comparison?
It's exactly what it is. It's a weak kind of gravitational lensing. But yes, we now use exactly this phenomenon all the time. I mean, it's clearly not the only proof of general relativity. As soon as that had been done once, I think Freundlich went and did another Eclipse expedition after the war, and it really tied it down. And of course, since then, it's just been tested to death, and relativity is very, very robust. We all use it every day in our GPS systems, because without relativity in your GPS, you'd be 10 kilometers out.
And yet, and I might be getting my wires crossed, isn't there a belief that there's something wrong with the theory?
Yeah, that's right. That's why people are dead keen to keep testing it by doing experiments like taking pictures of black holes and things like that.
Yeah. So far, it's held up.
It's held up perfectly, yeah. But if you can find a crack in it, then that opens up the possibility of new physics, which might one day unite quantum theory and relativity, which at the moment are irreconcilable, just like German and British scientists were.
Yes, well, I'm glad they sorted that out, because now we've got a nuclear age.
Quite so.
Yes. All right. You're listening to Space Nuts. Andrew Dunkley here with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, once again, a shout out to everybody who has joined our Patreon account, and we thank you very, very kindly. We have 13 patrons now, Fred, who are paying a little fee, just a tiny little fee every month to bolster our Space Nuts account, which has got 3 pence in it at the moment. It's great that people are willing to do that. It was an idea that came from the audience to create some kind of way of contributing. And so we do have that Patreon account at patreon.com/spacenuts. So thank you to everybody who's contributing to our little podcast. Also, drawing your attention to our YouTube channel. If you want to listen to current or back episodes of Space Nuts and you want to do it through YouTube, you can do that now. They're all on there, ugly mugs and all. We appreciate all the effort that people go to find us. We're on just about every podcast platform available. And I do sincerely want to thank everybody who listens, because our producer, Hugh, sent me an email the other day which I don't have handy at the moment, but it showed that our numbers are extremely good, and we're very, very pleased about that. And we just want to thank you for showing us so much support. It's just, it's fantastic. I'm so glad you like it, and so is Fred.
Indeed, I am. Yes. Thank you, everybody.
Nearly forgot you there, Fred. Now,
no, it's all right.
Let's answer a couple of questions, shall we? This one comes from Bo in Melbourne town. Hi, Andrew and Fred. I have a question about dark matter and dark energy. Are they interchangeable in the same way normal matter and normal energy are, as in E equals mc squared? Question mark. Is one way to test this to look at the correlation between the rate of expansion of the universe caused by dark energy and any decrease in dark matter over time from looking into early stages of the universe composition / matter-dark matter ratio? The answer is yes. Bye. I have no idea. That's a very complex question, but I kind of see where he's coming from.
Yes, and it's a very intelligent question, I have to say. Let's unpick it a bit, as they say in the literary world. Are dark matter and dark energy interchangeable in the same way normal matter and normal energy are, as in E equals mc squared, which is quite right. Matter and energy are interchangeable. And the answer is yes and
no. I was
no.
Right.
Yes and no. And the no comes from the fact that they seem to be unrelated. So, dark energy is not the energy equivalent of dark matter. They are quite unrelated. On the other hand, we suspect that dark matter does turn into pure energy because there should be how can I put it? Dark matter particle. We know that dark matter particles are some kind of subatomic particle. We don't know what they are. They outweigh normal matter 5 to 1, and they're everywhere, including here and there. So those dark matter particles can, we believe, interact with dark matter antiparticles, and that means a dark matter particle, but with the opposite charge. So it's like matter and antimatter. Normal matter, we know, has an antimatter equivalent. It's got an electron has got an equivalent which has a positive charge rather than the negative charge. And if you bring those two together, an electron and an anti-electron, which is usually called a positron, if you bring those two together, they annihilate and you get pure energy in the shape of actually radiation, gamma radiation. And so there is a theory that you might expect dark matter and anti-dark matter in some places to come together and annihilate and produce gamma rays. And scientists have even predicted what the kind of frequency of the gamma rays should be, the energy equivalent of the gamma rays. And so that's one of the things you might look for in the centers of galaxies where you expect dark matter particles to be close together. So that part of the question is right. Now, it's probably true that dark energy, when we find out what it actually is, might have a particle equivalent, because energy and particles are effectively the same thing. But at the moment, we don't know. And I've certainly never seen any kind of insights into the detection of dark energy particles. It's all, at the moment, looking at the whole universe and seeing the way it behaves. And so that sort of, perhaps it negates what Bo says in the second part of his question, which is talking about looking at the rates of change of dark matter and dark energy. Yes, people do look at that. What we find, though, is not so much a rate of change in the amount of dark matter, but a rate of a change in the way it clumps together. It was much more clumpy in the early universe and is less clumpy. No, I kind of put it the other way around. It was bigger clumps in the early universe and smaller ones now. And with dark energy, of course, we see that whatever it is, its effect on the universe has really only been visible in the last 6 or 7 billion years. And that's probably because dark energy actually wasn't strong enough to push apart galaxies that are stuck together by their own mutual gravity until the expansion of the universe had brought them further apart. That's not a very straightforward answer to a complicated question.
Well, it wasn't a straightforward question, I suppose.
Well, the first half of the question is yes, and the second half of the question is no. There you go. That's the answer.
There you go. Hopefully that half answers your question. But look, it's one of those areas of astronomy and science that is just based almost purely on theory at the moment, and we can't see this stuff, we can't find this stuff, we can't really understand this stuff to a certain degree, and it's going to take a lot of work over a lot of time to unravel it, I imagine.
Yeah, I think that's right.
But when the day comes, hopefully we're still around to be able to talk about it, because I think it'd be a pretty exciting discovery. And
it will.
As
and
you said earlier, it could open so many more doors.
Yeah, exactly. That's right. It will.
So time will tell. Hopefully not a lot of time, but you've got to be patient in astronomy, I've discovered.
You do.
Now, and space travel. Now, to a question from Christian Coddington. Hello, Christian. Thanks for your question. And thanks to you too, Bo. Christian asks, what conclusion... I love this question, by the way. This is the area that really gets me going. What conclusions could be drawn if DNA-based life were discovered elsewhere in the universe? What if the life discovered was humanoid? Would it be reasonable to then theorise that a more advanced civilization had either created mankind or spread their DNA across the universe for the preservation of intelligent life? I know this is is highly unlikely, but interesting to think about. He's been watching the Alien movie series, because that happened in one of those movies. They seeded Earth to create us so that they could feed the alien.
Oh, well, there you go.
Yeah.
I knew we had a purpose.
Yeah, that's not a very good one.
Yeah, we're sort of, already de-haired and quite tender looking to be cooked.
Just before Christian emails me and says, I've never seen Alien. It's very possible he's thought of this all by himself, and I don't doubt that, but it did actually happen in the Alien movie series. I don't remember which one.
So that is an interesting question. I mean, it points me, though, towards a more fundamental question, which is if we do, say, within the next decade, find microbial life on Mars, and either fossilized or living organisms, and we can analyze its genetic makeup, if we find out that it has the same genetic origin as our own genetic makeup, then that suggests that we're part of the same species, or not species, but the same genetic fold, so that we're not, you can't really imagine that you and I would be related to people or to organisms whose working fluid was ethane and methane and breathed hydrogen and ate.
The same universal petri dish.
That's right. But it's got to be the same kind of organisms within that petri dish. So if we find that, then we would probably assume that there'd been some sort of transfer of genetic material between the planets, that Mars and the Earth might have a common origin. On the other hand, if it can be demonstrated that those microbes have got a completely independent origin, and that might be that they're basically a different type of life, one that doesn't use water as its working fluid, for example, then that's what would be called a second genesis. And the second genesis idea is that wherever you have the right conditions, you get life forming. Now, we've got no evidence of there being a second genesis. In fact, there's really only one common ancestor for all of us on Earth, and it's probably a microbe called Luca, the last universal common ancestor, which is one reason why people believe that perhaps higher organisms might be very rare throughout the universe, even if microbes aren't. But, if you go then up the evolutionary scale to the kind of things that Christian's talking about, if we found a humanoid species with DNA-based life, then you might very well make the conclusion that it came from a common origin. It doesn't necessarily suggest that we are the food supply of some higher alien species, but it might well suggest that sorry, it wasn't Frank Drake. It's Enrico Fermi who asked the question, "Where are they all?" Because he expected life to be teeming throughout the galaxy if life is common. That might be an end product of that. And the reason why he's asking where are they all is because they could colonize the galaxy very quickly. I mean, by very quickly, I mean 100 million years or something like that, 200 million years, which is a long time in evolutionary terms. And we would change quite a lot in that time as humans. But it would still be reasonable to theorize, exactly as Christian says, that perhaps we were descended from a more advanced civilization, or we were descended from a more primitive civilization and have gradually evolved to the state that we're in now. I'm not sure that you can draw that big a conclusion from it, but it would certainly be very, very dramatic as news if we found people with 2 arms and 2 legs and DNA similar to ours.
In fact, I just thought of another film that Christian might have drawn his question from, and I can't remember. I always mix these two up. Mission to Mars or Red Planet, where they discovered that the face on Mars was left there as a test for an advanced race to unravel and discover their origin. As it turns out, Earth had been seeded by Martians who had been forced to leave their planet due to an asteroid impact, and they went off into another galaxy somewhere, and we figured it all out by visiting Mars and unravelling the DNA question that they had created in their face. There you are.
There you go.
So that might have been where Christian was inspired, or he just thought of it and went, I wonder, which is where a lot of my questions come from. Okay. Hopefully we covered that for you, Christian, and that your theory has been resolved. Probably not, because we don't know if anything else is out there beyond what we have in physical evidence of life, and that is all on this planet. However, Fred, thought came to mind while you were talking, our solar system alone, which we have access to, could actually offer some of that potential evidence, because there are planets and moons that have different environments and different liquid components that may contain life that has a different basis to what we know and love.
That's right. So that's what I was thinking of when I mentioned, ethane and methane-based life, because that's what's in the lakes of Titan, Saturn's moon Titan. Wouldn't that be extraordinary? It's not going to happen this week, but we might find eventually that we know the answer to these questions.
Yes, and hopefully within our lifetime. You never know. There are all sorts of missions being drawn up that are only on paper at this stage, but they may well get around to them one day, and then we might know. You just got to wait and see. And those ice moons are also looking rather delectable in terms of searching for life. So we'll keep an eye on those as well. So thank you to both Bo and Christian for their questions. We've got a whole bunch more to get through, and we'll work our way through them in coming episodes. And thank you, Fred, as always.
Oh, it's a pleasure. Always good to talk, Andrew, and I look forward to the next time.
Indeed. Professor Fred Watson, one half of the packet of nuts that puts this show together. And don't forget Patreon if you're interested in signing up for that, and listening to episodes via YouTube if that's your preference. That is now readily available. Until next time, from me, Andrew Dunkley, thank you again for listening to Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.
Thank you for phoning. Oh, hang on. It's Marnie as well. Just hold on a sec. I just should take that. Hello.